In this video, we're going to talk about the electric potential energy stored in a system of point charges. So our basic setup is that we have 3 point charges arranged in a configuration like so, and there is potential energy stored within these point charges. Now, just to make an argument as to why that must be true, let's ignore this charge for now and just think about these 2 charges. Well, there are 2 positive charges. If I assume that there's kind of like invisible hands holding the particles in these 2 locations, these 2 particles are feeling a repulsive force, and if we let go of those 2 particles, they will move apart from one another, right? They will be repelled from one another. They will be trading the potential energy stored between them for kinetic energy as they are pushed apart. That's what potential energy does, right? If I have some object that is storing potential energy in a gravitational field, if I release it, it trades its potential energy for kinetic energy, and that's exactly what would happen if I took these 2 particles here and released them and allowed them to move freely. So we have potential energy stored in this system. Let's figure out how much potential energy we have stored. The equation that we're going to use in order to calculate this potential energy is given by PE equals Q times V. So here we can use the absolute potential energy because we have a well-defined 0 point for our potential energy, and that is at infinite radius. That is, when 2 charges are infinitely far apart, there is 0 electric potential and therefore 0 potential energy between them. So we can take the charge that we are bringing in and multiply it by the potential created by a charge already there. This could be the potential due to one charge, as we have here, kq over r, potential due to one individual charge, or it could be the potential due to multiple charges, and then we would have multiple terms here, as we will see, one for each charge that is creating some potential, some electric potential at the point of interest. Okay, so what we're going to do is we're going to imagine bringing in charges one at a time to this system. So we will begin by bringing in charge 1. So it starts infinitely far away. We bring this charge in and we place it at this location. All right, how much potential energy does that charge gain or lose as we move it from infinity to that location when there are no other charges present? Well, we multiply its charge by the potential at that location due to other charges. But there aren't any other charges around, right? There's no other electric fields here because these charges have not been brought in yet. So our potential energy to bring in one charge is 0. One way to think about it is if you have just charges out in empty space, with no electric fields nearby, you can move that charge left or right or up or down, however you want, and there's no change in the potential energy of that charge. It's just at 0 potential energy all the time, no matter where you place it. Okay, so we bring our first charge in and we place it right here. We don't have to fight against any electric fields to get there. There's no potential energy stored in just that charge alone. Now we're going to bring in our second charge, Q2. Now, Q3 is not here yet. We haven't brought that charge in. So we're going to bring, from infinity, we are going to bring in Q2 and place it here. Now, in order to do that, we need to fight against this positive charge. These 2 charges are repelling each other. We are doing positive work in order to bring them together. We are storing potential energy as we do that. How much? Well, we can use our equation here. Q2, the charge that I'm bringing in, multiplied by the potential at the location of interest of Q1, the charge that is creating that electric potential. So that's K times Q1 divided by R12 magnitude, where R12 magnitude is 2√2 meters here. Notice we don't care about the direction of that. We only care about the distance that we are the distance between these two charges. So that is 2 root 2 meters. Okay? So we can we can put in our Q1 and Q2 and get this expression here. It will have units of joules in the end. We've left a K here, and we're just going to kind of simplify all of our expressions at the end to save some calculator work, basically. Okay, so this gives us an expression for the potential energy stored in the system of Q1 and Q2. Now what we want to do is we want to bring in charge 3. Well, charge 3, when we bring it in from infinity, so I'll draw it here, I'm bringing charge 3 in. Now, it is feeling an electric field due to Q1, and it is feeling an electric field due to Q2. Both of these charges are influencing or creating an electric potential at that location. So the potential energy, the change in the potential energy of Q3 as it is brought in from infinity is equal to Q3 multiplied by the potential at its location due to charge 1. So we're dividing by R13, which is the vector that points from charge 1 to charge 3, which is this distance here. The magnitude of that vector is this distance here. Plus, we have the potential due to charge 2 at that location, which is K times Q2 divided by the magnitude of R23, which is the distance between charge 2 and charge 3. So we have potential due to charge 2 at the location of 3, potential due to charge 1 at the location of 3, and then we multiply that potential by the charge we're bringing in, Q3, and we get this expression here. Now, notice that this is a negative value for the potential energy contributed by Q3. That's because as I'm bringing Q3 in, it is being attracted to these two positive charges. It's being attracted to this charge here, it's being attracted to this charge here. When you are moving in the direction of the electric force, you are losing potential energy. So we started at 0 when we're infinitely far away. Now we have lost potential energy from what we called 0. So we are at a negative potential energy contributed by bringing Q3 into this system. So if we want to find the total potential energy stored in this charge configuration, all we need to do is add up the potential energy that was brought into the system when we added each additional charge. We didn't add any potential energy into the system when we brought in the first charge because there were no other charges there to begin with, right? We didn't have to fight against any electric fields to get our first charge there. Then we added charge 2. We need to consider how much potential energy we added or took away from the system in bringing charge 2 from infinitely far away into this location. And we got this value here. And then we had to consider how much potential energy did we gain or lose from charge 3 as we brought it from infinitely far away and placed it in its final location. And we got this expression here. We add all of these together. The total potential is just the potential due to each of these. And what you will find when you plug all of this in is 0.4 joules of potential energy. Now, an obvious question was, how did I know to choose particle 1 first? What if I started with particle 3 instead of starting with particle 1? Well, the answer is it doesn't actually matter. What you'll notice here is that we have a term that relates particle 2 and particle 1. We have a term that relates particle 3 and particle 1, and we have a term that relates particle 3 and particle 2. So there is, effectively, we have individually calculated the potential energy stored in each pair of particles. 1 and 2, 1 and 3, 2 and 3. 1 and 2, 1 and 3, 2 and 3. Right? So if I started with charge 3, for example, I would still end up with all of these same terms. I would end up with one term which links each of these particles, which tells me about the potential energy stored between a given pair of particles. I just find it easier to think about it in terms of bringing in one particle at a time and then doing the potential energy due to each of the particles that is already there. But it doesn't matter which charge you start with, you will always end up with exactly the same three terms and exactly the same potential energy stored in the full system. As a final note, let me just say that you can do this procedure for any number of charges. I did it for 3, but we could bring in a fourth charge and put it, say, at the origin, right? And then we would have to figure out the potential energy change of this particle here as it was brought from infinity to its final location. And we would get, for this particle here, 3 terms. We would get a potential energy from 1 on our fourth particle, from charge 2 on our fourth particle, and from charge 3 on our fourth particle. And then we'd have to add that in to our total electric potential energy here, and we would end up with some other value. You can just keep adding on particles for however many you need, where you just have to consider the potential energy due to each of the particles that you brought in before every time you bring in a new particle.